Salam sejahtera, I am Clarissa Ganimili and my matrix number is D122410456. And for today's presentation, we'll be talking on the windowing filters for digital signal processing. So, the overview of this presentation that we are going to touch in the windowing filter is that we are going to focus on the introduction, the objective, the theory, definition, characteristic, design method, application, and also the conclusion of the window that we are going to explain in a second. So, there are two types of window filters that we are going to focus on for today's presentation. That is, the first one, we're going to talk on the rectangular window filter, and also the second is about hand window filter. So let's look into the introduction of the windowing filters, which is it is a method in the FIR filter design for finite impulse response filter designs, and also it's for approximating ideal filter characteristic, where it is using the windowing filter, and also the infinite impulse response of ideal filters is frequently unachievable in real-world applications. And also in the Gibbs phenomenon says, it is undesirable oscillation in the passband and stopband due to the slow convergence of the Fourier series, which cause near discontinuities is one of the artifacts introduced by truncating these infinite responses. And also windowing filters is using to reduce the effects to make in a finite duration by using the window function, and also makes the filter performance to be balanced. So, for the objective of today's presentation is to explaining the concept of windowing techniques in FIR filter design, introducing to what the windowing techniques have to do in the digital signal processing, the comparison between rectangular and also hand windowing through the side lobe attenuation, which is called as suppression, main lobe width, and the frequency resolution. And also to discuss the practical real-world application of windowing in filters and demonstrate the rectangular and hand windows. Also, we analyzing the trade-offs in the rectangular and also hand window. So let's talk on the theory of the windowing filters, which is it is the method for designing the FIR filters by using the windowing techniques. And then an ideal filter, just like as low pass filter, cannot be directly implemented due to the infinite length of the impulse response. And also the infinite impulse response is also truncated by multiplying it by a finite length window function of omega n, which is in order to make the filter realizable. And also a finite sequence that resembles the optimal responses is generated by this process. And then the different window filter techniques also offer a trade-off between the side lobe attenuation and main lobe width, which the stronger side lobe suppression lowers spectral leakage, while a smaller main lobe enhances the frequency resolution. And the performance of designed FIR filters is impacted by the window selection. Let's talk on the definition of the windowing filters that we have chosen for this presentation and also the assignment, which is the rectangular window filter and also hand windowing filters. So the rectangular window filter is a basic window in the digital signal processing, which significant spectral leakage occurs at the frequency domain as the result of truncation, which maintains the original signal but at around discontinuities at the edges. as well as it has a 4 side lobe and also the narrowest main lobe, which leads to high frequency resolution. So basically, in the noisy environments, the high side lobes produces ringing effects and make it challenging to discern closely spaced frequency components. So the rectangular filter it is helpful in situation where resolution is more important than lead edge suppression and identifying closely spaced tone in clean signals despite this disadvantage. And also the rectangular window filters used as a baseline for comparing the performance of other window function in the FIR filters and spectral analysis because of the simple and ease of implementations of a rectangular window filters. So for the Han windowing filters, it is a popular window function in digital signal processing where it is efficient reduction of spectral leakage and provides better side lobe attenuation, which is it used in the spectral analysis, audio signal processing, and the filter design.
Thank you. Now let's dive into the specific technical characteristic of the windowing functions. We analyze starting with the rectangular window. As we can see, this slide, the weighting method for a rectangular window is the most straightforward. It applies a constant weight of 1 to all sampled within a specific interval and then abruptly drops to 0. This brick wall truncation in the time domain is what defines its behavior in the frequency domain. The most significant advantage of the window is its main loop width. It features the narrowest main loop of any windowing function, which provides us with highest possible frequency resolution. If you are trying to distinguish between two frequencies that are very close together, this is your best tool. However, the sharp truncation comes with a heavy price. The side loop suppression is quite poor, typically offering only about negative 13 dB of attenuation. This leads to high spectral leakage where energy from the signal leaks into adjacent frequency bands, potentially masking weaker signals. Furthermore, we observe a strong ringing effect, also known as the Gibbs phenomenon, because of that abrupt cut off in the time. We see oscillations in the frequency response. Therefore, the best use case for a rectangular window is limited to scenarios where frequency resolution is the absolute priority over leakage suppression. For example, when identifying closely spaced tone in a very clean signal. Moving on, the hand window, which we found to be much more versatile tools for general digital signal processing, unlike the abrupt cut-off of the rectangular window. The ARM window uses a cosine shape or bell shaped weighting. It gradually reduces the signal amplitude to zero at the both ends. This smoothing of the edges is the key to its improved performance. When we look at the main loop feed, we see the primary trade-off. It is approximately twice as wide as that of the rectangular window. This means we lose some frequency resolution. We can't see fine details as clear as we could before. But look at the side loop suppression. It provides much better attenuation with the first side loop level dropping to approximately negative 31 dB. This drastically reduces spectral leakage, allowing us to isolate frequency component with much higher precision and fewer artifacts. The ringing effect is also significantly reduced. The smoother transitions in the time domain produce a more stable and cleaner output waveform in the frequency domain. This makes the Hahn window the best use case for general purpose spectral analysis, audio processing, and especially biomedical signal analysis like ECG or EEG, where avoiding artificial noise is critical for accurate diagnosis. On slide 11 and 12, we have our MATLAB simulation result for the rectangular window applied to both low pass and high pass filters. In the low pass example on slide 11, you can clearly see the sync function in the impulse response. Notice the ripples in the frequency response graph at the bottom. This is a visual confirmation of the 13 dB side loop issue we discussed earlier. The transition from the pass band to the stop band is sharp, but ringing is prominent. On slide 12, we see the high pass version. Again, the narrow main loop allows for a very specific cutoff frequency, but the ripples across the passband are quite large. In a real-world audio application, this will translate to a coloring the sound or adding unwanted resonance to the higher frequency. Now, let's compare those results to our hand window simulation on slide 13 and 14. The first thing you'll notice in the top plot is the beautiful bell curve we mentioned. In the middle plot, the impulse response is now tempered. The value at the edges are more smaller than they were in the rectangular version. Look closely at the frequency response at the bottom of the slide 13. For the low pass filter, the ripples are almost entirely gone. The pass band is smooth and the stop band is much more quieter. Yes, the slope or transition band is wider. It takes a bit more frequency for the filter to fully kick in, but the overall signal quality is vastly superior. Slide 14 shows the Hahn high pass filter. The same characteristics apply a very smooth response with a minimum oscillations, proving why this window is favored for high fidelity audio and medical equipment. To conclude our presentation, our research into windowing filter has led to several key takeaways. First, windowing is an essential bridge between theory and reality. It allows us to take ideal filter with infinite response and turn them into practical, finite length filters that can actually run on digital hardware. Second, we have demonstrated that there is no perfect window, only the right window for the job. The rectangular window is the champion of resolution but victim of leakage and ringing. It is a specialist tool. However, for the vast majority of modern DSP systems, the Hahn window is the superior choice. Its ability to suppress side loops and eliminate the Gibbs phenomenon leads to a cleaner, more stable, and a higher quality output. Whether you are working on a heart rate monitor, a speech recognition system, or a high-end audio processor, the Hahn window provides the balance of performance and stability needed for a reliable result. And thank you for your time.